Alrighty, let's see what we got here. Gonna be an easy one today. Count square sum triples. A square triple is a triple ABC, where ABC are integers, and a squared plus b squared equals c squared. Usually these are called Pythagorean triples, but maybe they're just renamed now. Huh. Anyways, given an integer n, return the number of square triples such that a1 is less than or equal to a less abc less than or equal to n. So c is at most n. N equals 5. There's going to be 2 square triples, 3, 4, 5, 4, 3, 5. And here, n equals 10. There's 4 because 3, 4, 5, 4, 3, 5, 6, 8, 10, 8, 6, 10. Okay. Here, n is equal to or less than 250. So my first idea here would be that this is one of those kind of type um, static type problems where the answer is always kind of fixed based on the input, and the input is very finite. There's only 250 n values, and there'd be 250 return values. So this is one where I would consider pre-computing the answer space, the answer array, and then returning the value based on that answer array. So let's go ahead and compute the answer array, and this would probably be easily a kind of slow n squared operation, I guess, for now. So the first thing that comes to mind would be to get all the squares and check if the sum of two squares are equal to another square. So I'll say squares is going to be an array for I in range of 250. Squares append I times I. And then use A, B, and C as indices, kind of. No, yeah, A, B, and C, they're slightly one-off indices because A at index or 0 index is A equals 1. So um, answers is going to be an array. It's going to be an array. Sure, answers are going to be values, all possible values of C. So for every A in range, I guess 250, for every B in range A plus 1 to 250, kind of want to actually check to see if there's a set here, because I want to see if C is in the square set, or I can manually check it, I guess, with a computation. Okay, so let's say the total is going to be answers at A plus answers at B. Those are the sum of the squares. And then check to see if total is the square itself. So I think I do if, let's say, root is equal to, how do I do square root? Is it SQRT? Okay, SQRT total. If the root times itself is equal to the total, which means that the square root, because this is probably not an integer. Probably need to convert this to an integer. Square root is probably a yeah, I need to convert this to a integer. So if the integer version, which is the truncated version without the decimal, multiplied by itself equals the total, then that means it's a perfect square. Then answers, I think append total, all possible values of c squared rather than c. And then let's go ahead and just print out the answers. I guess total root can't be more than 250. Root can't be more than 250. Maybe I should do a break here. If root is let's see what to do. It does 1. I think maybe I can break here if total is bigger than 250 squared. Then break, because then it's just not possible. And go on to the next iteration of A, the next iteration of B. Yeah, I think so. Alright, let's go and print out what this gives me for answers. This index out of range. A plus 1. Oh, whoops, I'm supposed to use squares. Oops. 2. Okay, it's a pretty long list. All these are square numbers. That looks like maybe 160 squared. Okay. I mean, there should be at most 250 things right there, right? Is that right? There should be at most 250. Because C has to be a whole number between 1 and 250. Why does that look so long? More than 14. I did something really wrong. Oh. Yeah, this is every single square. What the hell's going on? So A is 1, B is A is 0, squares at A, squares at B is square root of 3, which should be 1. 1 times 1 equals this can actually work with 1. Squares of A should be 1 and squares of B should be 4, I think. Yeah, the squares. Oh, I have a 0. Okay, yeah. I definitely need to make this from 1 to 250. Maybe inclusive. 250 is just never going to work. That makes the thing 249. Okay. I think that's how I want it. 1 to 250. I can be at most 249. A here is the index. Okay. Okay, those are the right squares. 5, 169, 5, 3 plus 4, 3 squared plus 4 squared is 5 squared, 5 squared plus 12 squared is 13 squared, 6 squared plus 8 squared is 10 squared. Okay, those look right, actually. So 165, that's actually a lot. Didn't realize it was that much. Anyways, so those were the answers. Go ahead and sort the answers. And print these sorted answers. Is whether or not this is going to print out everything. It's not going to print out everything. Unfortunate. So I was just going to copy and paste it. Let's actually print out the squared number. I think I just want to print out C. So I think I append the root. And maybe that makes it short enough to be copied and pasted. Okay. So all this is kind of the work for let's go ahead and remove the print. And I'll say this is the pre-compute work. Pre-compute work. And I'll say answers is equal to answers is equal to this. Whoops. It's equal to this maybe I'll call this the C values. And if I have a given n, where n is, let's say, 5, I'd search for that within this thing using a binary search. And the index of that corresponds to half the number of triplets, because there's going to be like ABC and BAC as possible tuples. So I think I just return bisect left. Is it called bisect left, I think? Yeah, bisect left, passing in the array, the search value, actually is bisect left or bisect right here? think it might be bisect right, to be honest. Because I want the index after finding the thing rather than the index before finding the thing. My list and the search value. Okay. So I think it's bisect right. And then the array is called cvals. And the search value is n. So if it searches for 5, then it's going to find index 0. No, it's going to find index 1, since that's the right side of the right insertion of 5 into this list. If I search for 4, it would give me 0. Yeah, so I can give this times 2. Okay. Okay. All right. So, was there a faster way than doing this pre-compute work? I'm gonna say yes. I think there was probably some non-brute force way. Like I think there's some algebraic way of finding where the triples are and where the next kind of smallest triple might be. Using, I think something like if you rearrange a squared plus b squared equals c squared, you arrange it to like c squared minus a squared equals b squared, then that means that c minus a times c plus a equals b squared, which means that like the two factors c minus a and c plus a must have must combine to form a complete kind of complete or form some set of paired factors. So for instance, if I do 5 minus 3 times 5 plus 3, or actually 5 minus 4 times 5 plus 4, that gives you 1 times 9, where 1 times 9 is 1 times 1 times 3 times 3. So so therefore this thing is itself a square of 1 times 3. Or if you do 5 minus 3 times 5 plus 3, that gives you 2 times 8, which gives you 2 times, like 8 is 2 times 2 times 2. So you're doing the square of 4. So you can kind of extend that to find other things, like let's say 5 minus 4 would work. 4 minus 3 doesn't work because you're doing 1 times 7. But if you do 1 times 25, it would be something like 12 and 13. 13 minus 12. 13 plus 12. So it'd be 1 times 25, where you're doing 1 times 1 times 25 times 25. So it'd be 5 squared, 12 squared, and 13 squared are the triplets. So anyways, there's some algebraic stuff like that, and maybe some other ways as well to find the triplets without having to do this brute force thing. But anyways, given the problem, I consider the problem as having as being very static. The input space is very finite, n is less than or equal to 250, and maps directly to the return output space. Fixed answers to every input. Thus, this is a good problem to find the fixed output space / array and return based on that. To find, by find I mean pre-compute. So here, so part 1 would be pre-compute the possible values of C. Use an array of squares and iterate over them to use as combinations of a squared and b squared. And check if their sum is a square. And that's this part here. I think this is faster than actually multiplying a times a plus b times b each time. I think that does, yeah. Using memory in this way, I think is faster than the extra little bit of multiplication. I could be wrong actually. And then part B is sort the array, sort and print the array. Copy the array back into the code as a static array. And then C, use search for n in the static array and use the index as a kind of a half proxy for the number of triplets or tuples that can be formed with that C value. Right, so like if these are all the possible squares that would be C squared, then given n is, let's say, 10, then you're searching for how many times this has occurred, which is proportional to the index. So the index here is 1. I use bisect right to search for where 10 would be found, but after 10 would be inserted post that value. So 10 would be searched and return index 2. 2 would be half the number of triples because each triple has kind of the ABC version versus the BAC version. Anyways, time complexity, this can be O of n squared to pre-compute the array, the kind of C values array, but O of 1 to run the method after having pre-computed it. So in future iterations or in future actual calls of this, given this answer array, is going to be just O of 1. It's basic complexity. Oh, wait, not quite right. It's actually O of log n because it's searching it. Yeah. to run the binary search on the array after having pre-computed. Okay, base complexity, this is going to be O of O of n for the pre-computed array. I'm not quite sure what the maybe it is just, yeah, I don't know how the number of correct C values compares to the size of n. It might just be proportional. It might be a log n, maybe. Not sure how the amount of C values compares to size of n. Guessing it's proportional. So it would be